Hello and welcome to our presentation on the laws of thermodynamics. I am here with Logan Vandy Hatter, Daniel Baptist, and Owen Smith, who you will see later in the video. The point of today's presentation is to give you a lesson on the laws of thermodynamics and teach you a little bit about it. And right now you may be thinking, what are the laws of thermodynamics? And think no further. The laws of thermodynamics define physical quantities such as temperature, energy, and entropy that characterize thermodynamic systems at thermodynamic equilibrium. Now, if you're me, you may be wondering, well, what does that mean? I have no idea. So basically, the laws of thermodynamics describe how thermal energy acts and reacts in a given system within certain constraints. We will get into more specifics with each team member as they do their own law. But these laws happen all around us, from everything from touching a hot plate to watching ice melt, which is very exciting. And now on to our first law, aka the zeroth law.
Hello, today I'll be talking about the zeroth law of thermodynamics. So the zeroth law was created in the 18th century, which is later than the first three, and it was actually added on and originally thought of to be as the fourth law. But then that caused some confusion in the world of science. So then a man by the name of Ralph H. Fowler actually came up with the term zeroth law, which has now been used ever since. And that is because the zeroth law actually, it supersedes all three of the other laws. So it's pretty much the most important one. And so that's why it comes zeroth. And then, so the zeroth law states that two thermodynamic systems are in a thermal equilibrium to the third. So, right here. So in this picture, so this means an equilibrium. So that means A and B are in equilibrium, and then B and C are in equilibrium with each other. So that means that A and C are in equilibrium to each other, even though it doesn't actually say so. By the zeroth law, A and C are in thermal equilibrium because B is in equilibrium with C. So this law is actually still relevant today with the use of thermometers. And so like, let's take like the house thermometer as an example. Like, if you were to leave like a pot of boiling water out and a pot of cold water out, then if you leave it out overnight, then it'll actually become the same temperature because of thermal equilibrium, and because it'll be thermally equal because of the temperature that was set in your house.
Alright, so the first law of thermodynamics was first spoken to exact word by Rudolf Clausius in 1850, but not without the help of other scientists before him. The law states in scientific terms that the total energy of an isolated system is constant. Energy can be transformed from one form to another, but can neither be created nor destroyed. And this is basically just another rendition or another way of saying that it's the law of conservation of energy or of mass, but as it relates to heat and thermal energy. So pretty much the law says that thermal energy is not created or destroyed, but rather transformed as the system around it changes. And this can be quantified by the equation delta U, which is the change in internal energy, is equal to Q, which is the heat added to the system, minus W, which is the work done by the system. And for example, something that happens every day, like when coal is burned to heat up water to create steam and to move a turbine and then create electrical energy. Although the energy is transformed from thermal to then mechanical to then electrical, there is no energy created or destroyed in the process of all of this. So now on to Daniel with the second law.
So to start off with the second law of thermodynamics, I'll talk about its history and how it came to be. In 1824, Nicholas Klarnet theorized that the conversion of heat into mechanical work depended on the difference of temperature in an engine and its environment. And then in 1850, the second law of thermodynamics was formally formulated by Rudolf Clausius, in which he stated that heat does not flow spontaneously from cold to hot areas. For example, if you have two water bottles, the green one being the warmer one and the blue one being the colder one, when they touch, the heat will flow from the green to the blue, not the other way around. Heat naturally flows from hot to cold, not from cold to hot. And then in 1856, Clausius expanded on his definition of the second law of thermodynamics and defined it as delta Q over T equals negative N, in which Q is the heat, T is the temperature, and N is the equivalence value. And then in 1865, Clausius defines equivalence value as entropy, and that the entropy of the universe tends towards a maximum. Today, the second law of thermodynamics states that the entropy of an isolated system can never decrease. It can only increase or stay constant if all processes are reversible. And that isolated systems tend towards thermodynamic equilibrium, the state of maximum entropy. It can also help give us the direction in time, because time flows in the same direction as the increase in entropy. Let's take these stack of video games as an example of a system. Here they're pretty orderly and arranged in a pretty organized manner. Now they're all scattered about and pretty disorganized. By applying the second law of thermodynamics, we would say that this disorganized state came later than the neat and organized state that you saw earlier. The second law of thermodynamics can also be used to explain why it's impossible to extract all the heat from a heat engine and use all of it to do work. It's because it loses some of its heat to the environment, meaning some of its energy cannot be converted into work. The second law of thermodynamics also explains refrigeration. Since heat does not naturally flow from cold to hot areas, work is needed to do so.
Today I'll be talking about the third law of thermodynamics, which was found by a German chemist named Walther Nernst. He was born in Germany and he actually won the 1920 Nobel Prize in chemistry. So this law states that as temperature approaches absolute zero in a system, the absolute entropy of the system approaches a constant value. So this law basically defines what absolute zero is, and it ties together the concepts of entropy and temperature. But it does also, there's some controversy of whether absolute zero may be unattainable, and that should be explained in the second law. But it's still important, and it can only occur in crystal form. And if we can't get absolute zero, that means everything is moving due to thermal energy. And I have a diagram here of what entropy is, because I was honestly confused about what it was. But it's the measurement of basically randomness and how random things are in a system. And the lower the entropy, the more ordered and less random it is, and vice versa. So basically, high randomness or high disorder equals high entropy, and low randomness or low disorder equals low entropy. And an example would be a gallon of gas has low entropy, but when it's being burned or used, the entropy increases.
To wrap up this video, we've talked about thermodynamics and mainly the four laws that pertain to it. The zeroth law, which states that if two thermodynamic systems are in thermal equilibrium with a third, then they are in thermal equilibrium with each other. The first law, which states that energy cannot be created nor destroyed, it can only be converted into different forms. And then the second law, which states that the total amount of entropy within a system increases over time, and that the more energy is transformed, the more it is wasted. And then the third law, which states that as the temperature of a system approaches zero, the entropy of the system approaches a relative minimum. Since thermodynamics is a study of energy within systems, both its conversion and its ability to do work, it's important to learn about its laws, since it can apply to almost everything within the universe. Thermodynamics plays a huge role in our lives and can be seen in the workings of heating and air conditioning, refrigeration, insulation, power plants, and the list goes on. If you enjoyed our video on the 4 laws of thermodynamics and learned something new,